All right, so kind of started here. Make sure I'm recording. Yep. Yep. So what we'll be doing today, a little bit different than what we talked about last class. So we were kind of dealing with selection issues, missing data, kind of thinking about how that was going to influence the bias and the statistical significance of our coefficients. So we've got two more topics really left in the semester. So this week we'll be talking about panel data issues, at least in the context of what I'll expect you to be able to know. And then when we come back from break, we'll have a week where we do what we call instrumental variables. So really just two more topics of new material. And then that next week, that second week after we return from break, basically the two class periods, I'll have a final exam that likely will get posted between today and Thursday's class, so likely posted tomorrow at some point, which will be a practice exam. So start to giving you review problems, kind of thinking about that final exam. Okay? So the final will be everything we've covered since the last exam, but we're reusing a lot of things that we talked about before. So I said it's not cumulative in the sense I'm not going to be giving you the most softball type questions of like interpreting a very simple linear regression, but we're still doing interpretation of regressions, right? So it's everything we've covered since the midterm. So that second week after we return from Thanksgiving break, all review, 2 class periods of just review. And then I think if we pull open syllabus, I don't have this one off the top of my head. I could probably get close, but just to make sure I'm giving you the exact date correct. I believe our kind of final exam will be that Tuesday of exam week, a 2-hour time block right in the middle of the day. Okay. So we should have a lot more time to review and study for that final than we did for the midterm. Okay, so that bodes well. We'll be doing a lot more review in class. We'll have a lot more time to ask questions in class, basically 2 full class periods, as well as office hours during that week. Now, I'll let you know in advance, I teach 2 large sections of 251, which is basically 300 students of Kelly's freshman intro to econ. So my office hours that week before the exam week will probably be pretty busy. I will likely be able to carve out some additional office hours just for this class, and I'll let you know what those look like after we return from break specifically, so that you kind of have time to review and you're not sitting there waiting, with a bunch of students asking about basic microeconomic issues. So I'll have some additional office hours that week prior to the final exam week. So you'll have a lot of opportunities to kind of hopefully study this material as we're going into the final. I think in some ways that makes the final, it's harder material, but there's more time to review. It makes it a little bit easier in some ways than the final exam. Okay. Other than that, that's kind of where we're at in terms of the class. Any questions for me? I think other housekeeping stuff. That quiz is due by the end of the week. So those sample questions 5 kind of go along with that quiz. When you return from break, have one more quiz. All right, we'll be kind of after we cover that last set of material. So it'll likely be due that week where we're doing review. It'll be over what we talk about this week and then a little bit of instrumental variables. Okay, so we've got one more quiz. We've got 2 more in-class quizzes. So I'll likely use one this week and then use one that week we return. So that'll give us a total of 12 in-class quizzes. We've got 6 total quizzes, and there'll also be a 6th problem set. Okay, that 5th problem set we have currently, which is due when the end of the day tomorrow. Okay. So hopefully, if you have any questions on that, tomorrow is kind of your last chance to get those questions answered. I want you guys to see as many of these points as possible. So on this one, free to come to office hours tomorrow, ask any last clarification questions. I had a couple people drop by yesterday. Same kind of thing, that 6th and final problem set. Come in and ask me as many questions. I want you to get as many of those points as possible, setting you up to where the final is daunting. Okay. Any other logistical questions for me before we hop into material here? Okay. All right. Looks like the weather's scared off a few people. It's not even near as bad as it was earlier today. We will take a look at kind of thinking about, I don't want this to show up. Hold on. Is it doing this to me? Not what I wanted. Sorry. Around my screen. So, yeah. So when we're talking about panel data, up to this point, in some ways we've actually used panel data, but we haven't really exploited its value. Okay. So all a panel data set is I have multiple observations for the same individual, firm, country, but across several different periods of time. So a lot of times up to this point, all we've done with that, so I think even in the last problem set 4, which is now graded and those are kind of posted, once again, there's a lot of people, I saw a lot of questions answered that I didn't ask. Make sure you're kind of using the do files we use in class to answer those questions. Usually we've only kind of used year as like a control, right? Or like I think years old, the make of the model of the car in that problem set. But we're actually going to use panel data to see how we can have variation within the same individual across several points in time. And that gives us the power to do some things that a data set that was cross-sectional one period in time doesn't allow us to do. Okay. So we're going to have 2 different types of panel data sets. We'll look at them today. One will be balanced, one's unbalanced. So I think the base example I have, one of the things we'll look at is if I have test score data for students and it's across several different time periods, if I had a balanced panel data, this would be that every student in my data set, I have their test score for every single one of those years. An unbalanced panel would be, well, students move in and out of states, right? Sometimes they skip grade, like they don't take the test in a certain year. So an unbalanced panel would be, for some students, I might have all 4 years of their test scores, but for some, I only have 2. For some, I only have 3. Some, I only have 1. So unbalanced panel data is where for some of my subjects, or in my example, students, I don't have every single time period of data. What do you think is likely preferred? Balanced or unbalanced? Balanced. Let's think about why. If I have an unbalanced panel data, one student might account for 4 observations. Some students might only account for 1 observation. So they're different subjects. If I have 4 observations out of the entire data set, am I going to influence the results more or less than a student who only had 1? If I show up 4 times, the only other student show up once, am I having a greater influence on the results than that other student? Yeah, right? So that's going to be a problem because then some of our subjects are going to be basically skewing our results, right? So we'd like to have a balanced panel data. So the way that we'll start writing this out, it looks similar to what we've been doing before, a simple linear regression, but a little bit different. So I'm no longer just going to have observation I, right, for X and Y. This might be my test score data, Y, but it's for subject 1 or student 1 in time period 2009. But I might also have a test score observation for student 1 that comes from 2010. So I need to make sure that I'm running this regression where the Y variable is in the same time period as all of the X variables that I'm including as controls. Okay. So the interpretation would be basically the same, right? That I'm trying to understand the effect of a 1 unit change in X on my Y variable. It's just that the observations I'm using are now within the same time period. Now, there might also be some other controls that I have. So if I think about my student data, let's say I have a student and I've got a gender dummy variable. If they're identified as male, well, I guess maybe this isn't a good example. Hold on, I got to change my example a lot of the times. Let's say, let's say I've got a dummy variable for whether or not English is their first language. Well, in every single year, if they're identified as English being their first language, that's always going to be the same. Doesn't matter what time period I look at. So there's going to be some control variables I have for these students that don't vary across time. Some of them will, right? So maybe I'm thinking about test scores and I'm thinking about, I don't know, what their family's income was. Well, that varies year to year, right? So their income would be a variable for that student that changes over time. So I need to make sure I would have different values for that student at different points in time. For some things like, was English their first language? That's not going to vary across time for that student. So that control variable Z would always be the same, no matter what time period I'm looking at. So we don't include a time identifier along with that. I think as we work through more data sets, we'll kind of start to see these differences and it'll be a little bit easier to think about. So one thing that we can do with panel data is maybe I don't want to pick up what might be true about different students, right? If I'm looking at their family income and its impact on their test score, maybe that has a different effect if the student was already of relatively high ability, right? So what's one way I could account for the fact that this student is of high ability without actually having like a real measure of that? Well, if I have test score data from prior years, it's really like if I knew what their test score data was the year before, I could control for that by including that 2021 test score in my 2022 regression. Or what's one way I can do that? We call this first differences. So what first differences would do is it says, look, I'm looking within the same student, and what was the change in their family's income from 2021 to 2022? I'm going to use that change in income to try to predict what the change in their test score was. So my Y variable inherently, it's almost like I'm controlling for where they started. Where was their test score in the year prior? What is it going to be this year based off of what was the change in their family's income between those two time periods? So first difference regression, right, is I'm going to look at not just the value of the variable in that year, but the change, right? Now, for variables that don't change across time, so this is like, is English their first language? When I take the difference between, there it is. When I take, if English was their second language in both time periods, if that's the same, when I look at that difference should always be 0. English was either their first language or it wasn't. So I either have a 1 minus a 1 or a 0 minus a 0. So these dummy variables or these values that don't change across time, when I look at a first difference regression, what happens to those? They go away. By looking at this first different approach, I'm only looking at changes in variables that do change over time. Anything that would remain constant across time, I'm essentially controlling for that without even controlling for it. So notice Z might not be, was English their first language. Maybe it's all omitted variables that don't change over time, but I don't have data on them. But if I use a first difference, right, the values from 2022 and 2021 would both include those omitted variables. So when I take that difference, what happens? Those omitted variables are subtracted from themselves. It's almost like I can control for all these omitted variables that don't change over time without actually having the data. That is very good for us, right? Because now we don't have to worry near as much about omitted variable bias. Anything that remains constant across time, by using a first difference approach, I'm eliminating all of those additional variables that don't change over time without even having data on them, right? So here we're going to kind of look at what this, take a look at what this looks like with some actual data. But really the end result, the end regression we're going to run is the change in X and then the change in Y. We don't even need to have data on these other omitted variables that don't change over time, Z, because they just get kind of canceled out there. Okay. So what does this look like? All right. So we'll kind of start, probably do a lot more work in Stata here, bouncing back and forth this week and the week we get back from break. Oh, so I've got, let's see, we're going to look at my first difference. I'm going to make sure I get my global set correctly. Easy here. So this is my OneDrive, so we're getting that global path set correct. And now I can just start using that to open up my data sets. So this first one, we're going to look at, I just call it first diff, right? This is, we go to Canvas, should be this data set here. So I had in my original data all these different student IDs. I also had what their test score and what their grade size was in 2 different time periods. So I've got a panel data set. Now this is structured a little bit differently than what we'll end up looking at with panel data, but I'm just using this initially to think about these first differences to kind of show you how this would be, what this would look like. So for this student, I've got their 2026 grade size and test score. I have their 2007 grade size and test score. So instead of like just running a regression for 2006 or just running a regression for 2007, what I'm going to do is create these 2 variables. So one is going to be what was the change in their test score, and the other is what's the change in their grade size. So the question I have is, if I'm in a class with more students, I'm going to get less individualized attention from the student. So I might think that's going to have an impact on their performance, right? Elementary schools, high schools are all very concerned with this, right? Higher education is concerned with this, right? And so if I take this first difference and create these 2 variables, what I'll end up with now is this change, right? Oh, I need to make it a little bit bigger so we can see all this. If I can get this all on one line for us here. So I can now look at this student's change in grade size between the 2 time periods. So their class got 4 students larger, but their test score went up by 12. So I now have these change variables. All I'm going to do is run a regression of what their test score change was between the 2 time periods and what their grade size change was. So when I run this regression, right, I'm going to basically get, well, the change in grade size, what's the unit there? It's just how many more students were in my grade, right? So for every 1 additional student that my grade size increased by across these 2 time periods, what was the change in that student's test score? So if I have 1 more student in my grade, my test score went down by 0.013, right? Now this is highly statistically significant. So this would be an evidence that being in a larger grade level, like more students, I'm going to get less individual attention and my test performance will decrease. And I believe this was like a standardized test the state had. I think this was ISTEP data, if I remember right. Now, why is this way more powerful than if I just ran a regression where I had test score data and grade size? Because when I use this first different approach, what did I cancel out? Every other omitted variable that was specific to that student that didn't change over time. So if they remain in the same school district over these 2 time periods, I've canceled out every factor about those school districts without actually having the data. I canceled out what the average income in the county was. As long as I'm assuming that I have students in the same school district here, right? All this other data that I don't have that would be the same in both time periods for the student, I don't have that data, but I've essentially controlled for it. So my interpretation is now it's the change of 1 grade size, 1 more student being in my grade, impact on my change in my test score, holding constant everything else that didn't change over time. So that holding all else constant from a first difference regression, it's a lot more powerful of a statement when we look at these regression results. Okay. So this is, pretty simple, right? We're not doing anything too crazy here. We're looking at these first difference regressions compared to what we did before. Okay. Let's think about here. We'll come down. I've got one right here. So I'll change this instead to be the player shot data, right? So I'm just going to open up that player shot data that I put up. Should be on, Canvas, right? We're going to take a look at this. So usually when we open up panel data sets, it's not going to be nice where every column is a different year. So in fact, I've worked with some of this data where we're looking at players. So this is like player data from NCAA basketball, I believe, and some different statistics that we could calculate. But notice here, the same player, now instead of having separate columns, they're showing up as separate observations or additional rows. So I have the same player, but in 2 different years, okay? So this is generally what our panel data will download as, right? I manipulated the other one just to make the first difference kind of easier to think about. Here it gets a little bit trickier, okay? So one thing I can quickly do is see whether or not I have a balanced panel data set. right? So this would mean that every single player, I have the same number of observations. So what I could do is say, create this new variable that's just equal to 1. So I'm just going to create this variable in the data. It's equal to 1 for every observation. Right? I'm then going to use these commands we can start to use with panel data, which is BYS. So it's by sort. So it says, look at the data, sort it by that player ID. So even though these look like names here, actually they show up as blue, so they're not text. This is kind of some of the categorical variables. Even though this looks like a player name, each player is given a different number. Right? So I can still kind of use this as though it's a numerical value. It just shows me what the name of the player is. So by each one of these player IDs, I'm going to generate a new variable, which is add up for every observation I have for that player, by that player ID, add up the count variable. So if I had a player that had 4 years of data, when I add up that count variable, I get a value of 4. They're only in the data for 2 years, I'm getting a value of 2. So if I had a balanced panel data set, when I create this variable, what should the value be? For every player, it should be exactly the same number, or 4 if I had 4 years of data. I can't remember. It was like 2019, 20, 21. I think there are 4 years of data here. So I run this. I can kind of see, oh, some of these are 4, some of these are 1, some of these are 2. So right away, it looks like I don't have a balanced panel. What I can then do, if I just use the tab command, that'll tell me how many observations or how many players do I only have 1 year of data for? How many players do I have 2 years, 3 years, 4 years? Well, I can see here, I don't have 4 years for every single observation. I have an unbalanced panel data set. Right? So that means that the players who show up 4 times, they're going to influence my results more than those players who only show up once. So I might be a little bit concerned about using this. I want a balanced panel data set. Now, that's not always possible. And outside the scope of this class, we have ways to deal with unbalanced panel data sets. But for now, we want something that's balanced. Okay? So I'm going to come down here. And instead of looking at an unbalanced panel data, I'm going to open up this birth data by state that I also put up on Canvas, right? So we're going to open this up, right? This should be, let's make sure that I actually have it up there. Birth data by state, right? So I can do the same thing. I create a count variable, right? Just equal to 1 for every observation. Now my data is by state. So I'm going to say by each state, add up that count variable and create this new variable, which is the total years of data that I have. If I have a balanced panel data set, when I use that tab command, I should see I have the same for every observation. Now, if this is state level data, they have to report it to the government. Hopefully I have a balanced panel data set, right? So sure enough, when I run this, every state I have 6 years of data for. Right? So this is the way, if I asked you on a problem set, wink, wink, that's how you would check to see if it's balanced or not, right? I don't know what AI would tell you or try to create code for you, but this is how you would do it, okay? You just simply create this count variable equal to 1, and then by whatever group you're looking at, first it was players, now it's we're looking at each state, create this new variable that adds up the total of that one, that count variable, and then hopefully if it's all the same value, that's a balanced panel data set. So here, we've got a balanced panel data set, that's good, okay? So we can start to think about running regressions using this, okay? Any questions over that idea before we keep moving? I'm going to jump back to the slides here for a second. Okay. So, instead of using first differences, we have a really easy command and a powerful tool in Stata, which essentially will do first differences with just a slight variation of it. Okay. So let's think about, we go back to, I'm running this regression. I want to know X's impact on Y, but I've got these additional controls that don't vary across time. Okay. Well, I could almost think about it. Let's say these things that don't vary across time, they're specific to every state. All right. So it's almost like when I'm running this regression, whatever my original intercept was, this isn't really technically quite the right way to write this, right? Because when I have things that are specific to a state, how could I capture that? If I think that there's a different intercept for Alabama than there is for New York, what would I create and include in my regression? I would use a
state ID variable.
Let's think about it as simple as this. What if I just wanted to identify differences between states in the South versus the North? I would include a dummy variable. If I've got 50 states, I'd include a dummy variable for every state except for one of them. Right? So if I think that there's things that don't vary within a state over time, what would I really want to do? Include dummy variables for each one. So essentially what I would be doing is thinking about there's some intercept, right, for my baseline group, but then every single other state, I'd want to include a dummy variable. Okay? So instead of using a first difference approach, which would kind of cancel this out, what's another way I can capture all of the characteristics about my group or my state in this example that would like control for every other factor that remains the same over time? I could simply include dummy variables for every state. Or in my other example, a little bit weirder, but I could include a dummy variable for every single player. I'm essentially then going to be picking up all of these differences in the intercept for each state, right? So we can do that, right? So what we're going to do in stata, we'll have this kind of constant, right? But I'm then going to pick up a dummy variable for every single, right? Include dummy variable for every single unique observation in my group or each state here. I'm going to leave out one, right? Now, that's a lot of coding, right? Or I'm going to have to get pretty good at using loops, right? Or there's a nice, easy shortcut in stata that will include that for us. And what we call that is fixed effects, right? So fixed effects essentially creates these dummy variables for us. Now, what it does, just to be, you might see a question this, how many additional variables would it include? If I have 50 states, how many dummy variables will using fixed effects actually include? Well, not 50, but 9. It's always going to leave one group out, has to meet the same conditions we talked about before when including categorical variables, which is I always have to leave one out. Okay. So what is this going to look like, right? We'll hop back to that birth data. Let's see here. Be a little more efficient. So I could run this regression where I'm looking at what? The average birth weight in grams and the average year of the mother's age was when the child was born, right? So for every additional year older, the average mother was in the state, the average birth weight went up by about 14.8, right? So the older the mother is, the healthier the baby typically. Now, what's probably something I might be concerned with here, since I ran a simple linear regression, initially, as mothers are older, birth weight might go up, but as they get old enough, maybe the health of the baby actually goes down. I might want to look at some nonlinearities here, right? But let's just assume it's a linear effect, just for the sake of this example. I'm just kind of revisiting some of these things we've already talked about. Highly statistically significant, but what do I probably have a lot of? Omitted variables. There's a lot of things that change across states, right? Alabama looks very different than New York, right? I haven't used these fixed effects yet. So if I want to control for these things, the fact that overall time periods, Alabama has a lower on average income level than New York, right? Or has a lower on average, I don't know, different states have different programs on, like high school, you have to take like a child development class or something like that, right? And so if that varies across states, I might want to treat Utah very differently than New York, right? So I'm going to run that same regression. Now, one way that we've actually already talked about doing this is if I have the state variable and it's categorical, one way I can include a dummy variable for every single group is simply use that IDOT command, right? So my state observation here, if we actually look at the data, we're going to run into a problem, which is that, so this is a text, right? It's showing up as red. So when I try to run this, it's going to give me an error. if I run a regression, I have to use actual values. I can't use words, okay? Now, we know that I could just assign every state a unique number, right? And then I could run this regression. So one, I think we've already looked at this in some other context. But what I'm going to do is I'm going to include for this variable that came in as text, if I use the encode command, take that original variable, which was a word, but for every unique string of text, create this new variable, which is called state FE, or my state fixed effect variable, which will assign every single state a unique number. So if I run that encode command, it looks like I have the exact same data, but now every single state has a unique ID, right? I can now use this to include my fixed effects. So if the data comes in as a string variable, we're going to have to use this encode command, basically put a number to every string of text, but then I can use that I.dot command, right? So now when I use that I.dot command, notice if I have this encoded variable, it shows me that it included a dummy variable for every single state. I'm not sure which one it left out here. We could go through the list and figure out exactly which one it is, but it left one of them out. I just don't know which one, right? Which could be problematic if I was interested in, like, does South Dakota have a higher or lower, or Y variable is what, average birth weight than whatever the group is I left. I'm not sure what that state is, okay? But we've now controlled for what state we're looking at. So now our regression results, anything that is time invariant or doesn't vary within a state across time, we've controlled for. So what should happen to our coefficient? If we've now included controls for omitted variables that we didn't before, our coefficient should be different, right? We don't know in which direction, right? But it will change. So if I go back and look at my naive regression without using fixed effects, 14.8, once I've included all of these state controls, it's now -33. Completely different sign, right? And it's highly statistically significant just in the opposite direction, right? -33 as opposed to whatever it was before, 13, or what do we say it was? 14, right? So we can now control for all time invariant factors of that state. Now, another way of doing this is there's this areg command, and I can put A, and it absorbs kind of that state fixed effect variable I created. If I run this regression, I should hopefully get the exact same value that I found using the I.dot command. Yep, same statistical significance. It's just going to be, doesn't show me all of those dummy variables that it created. So in practice, people like to use the areg command because if I have states, I have to look at 50 coefficients. But if I used it on that player data, I'm going to have a dummy variable it shows me for every single player name. That's going to just be a long thing I have to scroll through. If I use the areg command, it doesn't show me that it created all those dummy variables, but it did. Right? It gives me that same coefficient without showing me that it had to include all those dummy variables. Right? So both of these commands will give me the exact same results. Okay? Any questions on that before we take it one step further? This is a little bit more coding stuff than it is like we're not really changing anything that we're doing here. Now, one thing that we're going to want to start to play around with, and that can be helpful for us for some later things we're going to want to do, I can also set up my data set as a panel data set. Right? I can tell Stata, look, I have a panel data set, and this is the subject, and this is the time period. Because we don't necessarily have to just do time periods, right? I could have a panel data set where I've got different states and every single county. Right? So it doesn't have to necessarily be across time. It could be across geographical regions, right? Now, most of all the examples we'll look at time. But here, let's think about, I'm going to set this panel data set up where I've got, I say XT set. So that tells Excel, I've got a panel data set. Treat this like it's a panel data set where that state fixed effects variable I created. So once again, I'll have to use a numerical value here. So if I started out with my original data and I just tried to use state, this XT set won't work. I have to encode that string variable so that it treats every state as a unique number. So it's going to be, here's my subject, this unique state identification number, and then year is the second part of that panel data set. Now I'm going to use xtreg, so just run a regression with a panel data set. But now instead of having to include IDOT or absorb, I'm just going to put this comma FE. So what this does is it tells data, here's a panel data set, use fixed effects or whatever the subject is, or in our case, the state, right? We have several different time periods, but they might all come from the same state. Control for what state that is. So when I run this regression, what do I see? The exact same result. It's just a different way of running that fixed effects regression. It doesn't show me all the dummy variables that it included, which is kind of nice. And it gives me a bunch of other statistics that we're not necessarily going to focus on for right now. We're just focusing on it's giving us that same coefficient and the same statistical significance. So notice we go back here, test statistics from all those forms was the exact same. Okay. So 3 different ways of really doing the same thing. Okay. Any other questions before we keep moving here? So another way of thinking about these fixed effects is essentially I'm controlling for the average, right, of each state. Controlling for all the factors that would influence the average Y and X variable, so birth weight and mother's years of average age of the mother across these observations. So another way I could do this is I could essentially demean the data. So for every state, take out the average, right, mother's years mother's age for that state from each one of those observations. Okay, that's all a dummy variable does. Is it controls for the average of that group. So if I instead went through and I set this up as a panel data set just to prove this to myself, by each state, I'm going to create the average birth weight, which is just the mean of the birth weight in that state. So this by sort command, right, says by each state, just take the observations from that state and give me the average birth weight of just the observations from that state. So if I run this command, and then I look at the data, notice for Alabama, it gives me the birth weight average of Alabama across all periods of time. And then for Alaska, it gives me Alaska's average birth weight across all periods in time. And then so on and so forth. So I can do the same thing and create the mean of that mother's age variable. Does a similar sort of thing, right? What I'm then going to do is go through every observation and take what the actual value was and subtract that state's mean. So what these fixed effects essentially do is what we call demeaning the data. But it doesn't demean it from the overall mean. It only subtracts the mean of each individual subject, or in our example, each individual state. So if I created these variables where I took birth weight and I subtracted that state's average mean across this 6 years of data, and then I run a regression with that birth weight minus the average and the age minus the average, I don't have to include fixed effects. That's essentially what my fixed effects are doing. It's controlling for the average across these time periods for that subject, or in our example, the subject is the state. So hopefully, if I demean this data and run a regression with the demean values, I get the exact same coefficient. And really the fourth way of running these fixed effects. Now, why might that last way not be very practical? So I had one X variable here. What if I had 50? I'd have to demean every single one of those variables, right? So you're actually going through the process of demeaning. We don't have to do that, but we can kind of prove to ourselves that that is what fixed effects are doing, right? Now, the easiest way to do this is probably to set this up as a panel data set and use this comma FE command. That's going to be what you would see most people in practice using, right? Or what you would want to use to be efficient. Okay? So I'm getting a little bit into the weeds in terms of like efficiency of coding. There's really 4 different ways of doing the same regression here. This is going to be the one that's often preferred, right? Because it just takes the least amount of time. Okay? Any other questions or to keep moving here? Okay. What do I want to do? Where are we at? Okay. All right, fine. So just to kind of solidify this idea, when we include these dummy variables, like if I think about, here's my regression I want to run, here's what the averages of those variables are. Well, the average of the constant for every single prediction would just be the constant. So that should just be the same thing here, right? So when I subtract, when I demean the data, right? Notice my constant goes away. My error term, I'm essentially demeaning that error term as well. But this to me just looks like an error term in the regression. It doesn't look any different. So when we look at demeaning the data, it essentially, the reason why it works is because essentially it was controlling for any other factor that was time invariant across these states. Right? So this is kind of the support behind why demeaning works, because when I look at that mean equation, the mean of my constant would always just be my constant. So my constant minus the constant, it cancels it out. Right? Now we don't have to worry too much. I'm not going to ask you questions about this, but this is why demeaning works. We kind of already looked at this. Autocorrelation would be the next thing that we talk about. But I think I want to focus a little bit more on here since we're talking about it. Something that's a little bit different. So this is the example that we just stopped on. Okay. So maybe I think that there's things that vary across states that are going to influence my results. And I don't have a lot of data on that. And so I want to control for anything that's constant within a state across time. Now, what might be more likely to be true if I have national level policies that impact all states, right? Then where is my variation going to be? So if there's national level policies that change year to year, but impact all states, what fixed effects would I actually want to include? So for all states, things are going to be the exact same. So shouldn't control for the state there.
You ask if they're all treated equal in.
Yeah, if the policy, the national policy is the same for all states, but those policies change year to year. So when I think about the number of dollars given to the health sector, that changes year to year, right? But if the government is giving that out proportional to states' GDPs, it's treating them all the same. What I actually want to control for is not variation across states. I have something that's impacting my observations across time. Now, it's the same for each state in every single time period. So what do I actually want to include fixed effects for? Not my state, but for my year, right? So all I would do, this looks very similar when I'm doing this in Stata. I'll set this panel data set up. But if I think that there's variation that is constant instead of within a state across time, it's constant across time, constant within time across states, right? Then I'll just set up my panel data where the subject is actually the year, and the kind of variation in the year is going to then be across kind of these different states. So all I'm going to do relative to what we did before, I want to include this here. Where did I stop here? There we go. So instead of having it kind of set up the same way we did before with year and state, now I've got I'll skip down too far. Yes, sorry. This would help make a little bit more sense. Sorry, where were we at up here? We stopped right here. This makes a little more sense. There we go. All right, so before we had this set up where I had the subject was the state and there was variation across years. Right? Now I'm going to think about, I want to set this up so that there's variation across the years, right? But kind of every state is treated the same by that. So instead of having this where my subject is the state and then the variation within state across time, I've now have this set up as the subject is the year, and there's variation within each year across these different states. Okay. So when I include my fixed effects control now, it doesn't include a fixed effects for the state. It includes fixed effects for whatever my subject is, right? That first kind of word that I identified in that XT set. So before we had like state observations and then each time period. When I set this up where I put the year first, right? I'm now kind of thinking about within the same time period, I have variations across these states, right? And so now when I include that fixed effects command, I'm running the same regression, birth weight on mother's age, but I'm now not going to include dummy variables for every single state. I'm going to include dummy variables for every single year. Okay? So it's just controlling for something else, right? It's including a different set of dummy variables. So it kind of depends on the question I have, what fixed effects I want to include, right? In this example, probably makes more sense to do it the first way that we did it. I think there's probably a lot more things that are constant within a state across time than there are things that are constant within the same year across states. But if we had a different example, maybe that's how we want to do it. So I include fixed effects here. Now notice I don't see the same coefficient, right? Because I've included a different set of controls. It's not controls for what state I'm in, it's controls for what time period, right? So I could do this kind of in a similar way using the IDOT command or the AREG and using the A command with year. It's just basically using a different set of controls, okay? And we could do the demeaning stuff here as well. I won't kind of waste too much time on this. It's really the same thing we did before, but instead of creating these means by state, we're creating them by year. So it really depends on what we want to include fixed effects for, the way that we have to set this up. But if whatever you want to include fixed effects for, that's what's going to be that first word in your XT set command. All right. So if I want year fixed effects, I need to set this up year by state. If I want state fixed effects, I have to set this data set up by state by year. Is that clear? Any questions on that? Okay. Think here. Anything else that I want to go back to? I think we'll call that here. So this is where we left off, just to kind of have a marker. I'll think about GDP. What if I want to do both? Okay. So I don't think I have anything in the slides for this. All right, so we're going to kind of stop here, pick up on the slides probably next class. The rest of what we're going to do today is in Stata. So I originally had this data set, and I think that it was just way too large. So I gave you one. You can ignore this portion of the code. This was me creating the data set for you guys. So the data set that you will see on Canvas is this GDP class data. Okay. So if you're working along with me on kind of this do file, we're going to kind of skip this because this was like a huge file. And when I tried to upload it to Canvas, it got really mad at me. So I had to scale it down a little bit. So we're going to use a smaller version of it, which is the one that I posted. So we'll kind of use this GDP class data, opens it up, take a look at it. So here I've got, I called it GDP, is the average income, right, of these different counties in different states. Okay. So the first thing I'm going to do is run this naive regression where I'm looking at how is the unemployment rate of a county impacted by the average income. I'm not including any fixed effects here. I'm not controlling for anything else. And I get this very naive regression coefficient of negative 0.07, but it's highly statistically significant, right? So when average income in an area goes up, unemployment tends to go down, right? It attracts more businesses, et cetera, okay? Now, I'm going to set this up. I don't have to simply use I don't have to use like subject and year, right? I've got a data set now where I have many different states. Within each state, I have many different counties. But then for every county, I have multiple time periods collected. So I can actually have like multiple levels of panel data, right? So here I don't just have state by year. I've got state by county by year data. Right? So I don't have to just use two levels. I can use all three. Right? So I've got state and county fixed effects. right? The problem is if I kind of try to set this up, right? And I try to include fixed effects, what is it going to include fixed effects for? So I can actually just show this to you here real quick. So let's say, excuse me. So I want to look at unemployment rate, income, and I use that fixed effects command. Too many variables specified. Okay, well, I've got a problem, right? So when I have this fixed effects, if I have multiple levels here, I can't like use it in the xtset command. How could I create a new variable based off of state and county to like mold them into one? So remember, what did we originally do when we had string variables? I had to treat every string like it was its own number. So instead of having like a different number for every state, I now want a different number for every unique state and county combination. So what we can do is say, okay, look, by state and county, create a variable that is equal to 1, right? This will just set the very first observation of that state and county equal to 1. So I'm going to go ahead and do this, right, and kind of show you what it does in the data. So notice it sorts it. That by sort command is nice because it makes the data easier to look at. So for Autauga, I don't know how the hell to say that, Alabama, whatever that county is, across these different years, there is only one, the very first observation, the very first year, it puts a 1 there. And then for Baldwin, Alabama, for the very first observation, it puts a 1, 0 for the others. Okay. So I've identified kind of the first observation for every county. What I'm then going to do is by this unique variable I created, sort the data by that. So what that's going to do is it's going to put all of those first observations from 2011 all like in sequential order by county and state. I'm then going to create this state county ID where when I put underscore N, it says take the first unique state and county, put a 1. Take the second unique state county, put a 2, 3, 4, 5, etc. So when I run this, I can kind of see what did it do. Okay, it grouped the data. Here's all of these unique equal to 0. All of those unique observations were identified the first year of every unique state and county. If I can get there. Rolling, here we go. Excuse me. For what? Citrus, Florida, it identified that with a variable or with a value of 1. Pierce, Georgia, that county gets a 2. McCreary, Kentucky, that got a value of 3. Every state, unique state and county gets a different value. Well, I still have a bunch of missings here because it only did that for the first year of data. Well, if Citrus, Florida is always 1, I can then just go back to say, okay, by state and county, take the maximum of that state county ID I created. So I first will create these unique numbers just for the first year of observations. I will then take that number and put it in for every unique state and county for all time periods, right? So when I do that, I've now got King, Texas is always 799, right? And I've got that Kimball, Texas is always 2087. So I've now created this variable, which is a numerical value that identifies every single unique state and county. So if I now think that there are traits that are specific to a state and a county, what I can essentially do is control for those by including fixed effects, right? So now that I have this new identifying variable created, I come down here. Before we said it gave me an error when I tried to set this up by state, county, and year. Well, it doesn't mean I can't do it. It just means I had to create one single variable that was a unique state and county ID. Now I set this up by unique state and county ID and year. I can include state, county, fixed effects. Right? Now I'll take this out for a second just to kind of show you. Here, what it's doing is I'm now getting results that included fixed effects for that unique state and county. Now, maybe I think there's things that vary, or sorry, there's things that I don't think vary across a state, county, or across a unique state and county combination across time. I've included fixed effects for that. But I also know there's national level policies, and I also want to control that there's variation that I might only see, might be constant across all counties, but vary across time. Or sorry, it might vary. It might be constant within the same time period across all these state and counties, or I might want to include year fixed effects. So I can actually kind of create, I might try to do this, oops, by using that IDOT command. So what this should do is it includes fixed effects for that unique state and county, but also fixed effects for the year. So I can really kind of create two levels of fixed effects, right? So in this one, I use the fixed effects command to create that state county, those dummy variables. I then use the IDOT command because remember, we said when I use FE, it only creates dummy variables for that first word of the XT set or whatever that group is. If I also, on top of county, unique state county fixed effects, I also want to include dummy variables for the year, I can still do that, right? Using the IDOT command. So this would be kind of like two levels of fixed effects, right? So here I'm controlling for the year, anything that doesn't vary across those states within the same time period. I'm also controlling for anything that doesn't vary across time periods within the same county. That's a lot more powerful. That's a lot of things I didn't have data on, but I'm now holding constant. Okay. So fixed effects, ultimately with panel data, we just avoid, like if you had to summarize this, we are avoiding the omitted variable bias without actually having the data. All right. We can control for all of these other factors that are specific to whatever we're including these fixed effects for without any data on them. So that's an example of kind of, you would kind of think about maybe this as like two-way fixed effects. And notice like that coefficient looks very different than when I only included state county fixed effects. And that looks very different from the original naive regression, right? We went from negative 0.07, negative 0.24, where when I include fixed effects for both of them, I now see that that effect of income on employment is no longer negative, it's actually positive, right? And that's more powerful and more accurate because I've now controlled for all of that omitted variable bias, right? Anything that would have varied across counties, across counties within the same time period and across time periods within the same county. Okay. So it's kind of one way we can kind of get at this. Where are we at in time? We got 15 minutes. So what do I want to do here? Oh, we can look at this stuff next class. It's a little bit more specific to that. Might be taking it a step far. So let me see what else did I put in here. So I put GDP fatality data. Any questions over anything up to kind of this point? So a lot more of this stuff would be specific probably to like a problem set, where we're thinking about kind of how do we include these controls? How do we include these fixed effects, right? Any questions over anything, or what if I had this, or what if the data set looked like this?
Yeah, how would this even be on the exam?
How would this be on the exam?
Yeah.
So
It'd be a lot of different things to see on the exam.
Huh?
Be a lot of different variables to see on the exam, right?
So I could phrase it this way. Let's say I go back to that player shot data. Maybe I'm thinking about if I had this data set and I set this up. So I have what? Player ID by season. So I'm going to set this up as a panel data set, right? Maybe I'm interested in the impact of, what variables do I have here? So free throw made, and let's go to attendance. So whether or not the free throw was made and what the attendance of the game was, right? If I think, right, that attendance, right, might create pressure. So someone stopped in my office yesterday and we talked for probably longer than they wanted to about some research I'm doing. But basically, we're using sports data to think about labor markets. In high pressure situations, do CEOs or do workers perform better or worse? So attendance is a measure of pressure. There's more people, my performance might actually go up if I'm more focused on my task, but I might also panic like on an exam when there's increased pressure and I might do worse, right? So that's all we're really trying to get at here. Now, if I wanted to include player level fixed effects here, so this could be a question I ask in the exam, right? I have this regression, I want to include player level fixed effects. What should that control for? Things that are specific to that player that do not vary across time. So I might say, or the quiz, like leave these blanks, right? But if I include player level fixed effects here, I'm controlling for factors that vary across seasons or time, right? If I include player level fixed effects, what I'm controlling for are things that do not vary in this player across seasons, right? So when I think of things like, I have some variables in here, like height in inches. Well, I mean, I guess technically some of these players could grow in their early 20s, but for the most part, they're already the height they're going to be, right? Those are things that even if I didn't have data on, including those fixed effects, I'm controlling for that. They're time invariant factors that they would vary across time. That would not vary across time within the same player. Okay? Now, if I included season level fixed effects, those would be things that don't vary across players within the same time period. So I could ask questions about kind of these different types of fixed effects and what we're controlling for there, right? So the player level fixed effects would control for things that do not vary across seasons for any one player. Time or season level fixed effects would be controlling for things that don't vary within the same season across players. Okay? So I'm kind of controlling for things on different dimensions there. But you're right. There's probably not as many specific questions in terms of there'll probably be, and when you're thinking about the exam, bulk of the questions are going to come from probably stuff we've already talked more from some of the other sections we've talked about. We're probably going to spend a little bit less time on this. Like we'll probably even start instrumental variables on Thursday's class a little bit. I might go back and review some more of this nonlinearity stuff. But that would be kind of like one level of question I could ask, right? Or I might ask a question like, just to kind of get conceptually what we're doing, if I included player level identifier, the player level fixed effects here. So I put in comma FE. And let's say I told you there were 3,000 unique players in this data set. How many dummy variables am I going to have on that right-hand side? So if I use player level fixed effects, like I said, I run this regression. I guess there's not 3,000, there's what, 12,000? How many dummy variables would actually get included here? 12,218. I have to leave out one. So there might be some simple questions that come from this fixed effects chapter. I also might want to think about what is including these fixed effects going to do to my R squared values. So if essentially I'm including 12,000 dummy variables, when I run fixed effects models, what is almost guaranteed going to happen to my R squared? It's going to go up, right? So if I think about a regression like this, where did I leave off here? So let's run a naive regression, and then we'll run the fixed effects just so we can kind of compare and contrast. Notice, what's my R squared here? 0.0007. Notice here, my R squared actually doesn't go up by much. I can't even see out to a certain decimal. So without even being able to see it to the fourth, what do I know for sure is going to be true about my R squared from this fixed effects regression? Even though it doesn't look different based off the statistics, so maybe I showed you both of these regression results, what do you know has happened to the R squared? Has to be higher. No, I can't see that it's higher out to the fourth decimal, right? But I know by the pure fact, once again, not cumulative, but comprehensive, if I include more variables on the right-hand side, what has to happen to my R squared? Has to go up. Right? Now, what is a drawback if we want to think about this with my fixed effects regression? So if I'm talking about my adjusted R squared, that is 1 minus the proportion that we can't explain times n minus 1 over n minus k minus 1. Well, if I'm using the same data, n doesn't change at all. But when I run fixed effects, I'm including, in that example, 12,000 dummy variables. What's happening to k? What did k represent? The number of control variables. So k is going to go up. What would then happen? I'm subtracting a larger value. So this is going to go down. So this fraction would be higher. If I'm subtracting a larger value, my adjusted R squared will be significantly lower, right? So although we like fixed effects because we control for these omitted variables, when it comes to like model fit, thinking about our adjusted R squared, it's going to be penalized quite a bit by the inclusion of fixed effects. So we better make sure that we're eliminating some significant omitted variable bias, right? Because we know that we're going to suffer in terms of like what our model's explanatory power is.
Isn't the adjusted R squared here like not necessarily important actually?
My adjusted R squared?
Yeah, in terms of our interpretation, like we're trying to find the specific.
If we're just concerned with the coefficient,
yeah,
right? This has nothing to do with whether or not one specific coefficient is biased or not, right? But in terms of model fit, it's very important. In fact, the way we determine whether or not we want to use a log-log, a squared model, a cubed model, a fixed effects model, what should we really be comparing? One statistic we can always look at, that adjusted R squared, right? As long as we have the same dependent Y variable. The adjusted R squared was always telling us whether or not we had a better model fit, right? Once again, with the caveat that we have the same Y variable. Now, I'm keeping it simplistic here. So when we're looking at these coefficients, I'm controlling for some omitted variable bias here. But if I have other variables in my data set, I can do the same thing and also use, I don't just have to use fixed effects. I can use fixed effects and also include controls for, what here did I have? Just to make a simple example here. Division 1. Now, I'm gonna have actually, can I use anything here? I think I'm actually gonna have a problem. I can use here's a good example. This might get at some of what we're doing as well. So year in school, right? So this is if they're like a freshman was a 1, sophomore 2, etc. So I can use additional controls and still run my fixed effects models, right? So in practice, I can use fixed effects, but still control for things that, well, fixed effects only control for things that didn't change over time within a player. Well, the year I am in school will definitely change across seasons, right? Or, maybe my height or my weight changes, right? Or maybe my number of minutes played changes season to season, right? So I can still control for things that vary across time. Fixed effects simply controls for things that do not vary across time for that player. Now, if I try to run this fixed effects model, I'm going to try to make sure I choose one here. Let's do, that's not going to necessarily change either. If I had, so I know that none of this will work, but let's say I have like this variable of just to connect the things we've already talked about. I think that these height variables come like they're measured each year, like the NCAA. And so some players, there will be variation in their height. Let's assume I had a data set where all these players don't change once they play one game. Their height is the same across every year in college. If I include fixed effects for each player, if their height doesn't change, that should control for that. So if I try to use height as an additional control, what issue would I run into? So if the player is always the same height in every season, and I've already controlled for everything that is time invariant for that player. If I try to include that player's height, what issue did we talk about before I'm going to run into?
Multicollinearity.
Multicollinearity, right? So if I try to include variables that are time invariant, and I've already included fixed effects, I should get yelled at by Stata. It's going to drop those variables. Now here, I can't show you that because I know what happens is there's going to be like a handful of players where their height changed in one of the years. And so it can still actually have, it's not perfectly multicollinear, but I still need to be thinking about what is fixed effects doing. It's including all these dummy variables. I still need to be concerned with things like multicollinearity. So I can't include controls for things that don't vary across time, but for things like their year in school that do vary across time, I can still control for those. In fact, here I could probably even do things like division one, I think was a variable because some players change schools. So that will also be vary across time. So I could include that as an additional control as well. Once again, I can include things that are time invariant, and I can also control for things that do vary across time within the same player. Now there are probably very small number of cases where that happens, but there still is some variation there. But if I had something like height that was the same in every single time period for every player, there I would have multicollinearity issues, right? So we still need, we can think of fixed effects. Overall, it's just like we were on our own, including these dummy variables. So we would still run into kind of similar issues that we talked about before. I know I went kind of with tangents, so what the original question was, but this is just thinking of like different things we could do with these models. Oh, the adjusted R squared. We talked about that a little bit. But notice, as I include additional controls, I'm also going to see that coefficient change as well. Once again, it doesn't take care of every single omitted variable bias when I include fixed effects. It only controls for the omitted variable bias of things that are time invariant. And there's plenty of other statistics we're not going to dive into here that it gives us from these fixed effects models. I'm kind of simplifying it here and keeping it pretty basic. Okay. If there's anything else, I think that can kind of leave us in a good place to kind of end on. We'll talk about next class some additional issues that we run into with the error term when we're running these fixed effects models. We'll probably look at just a couple more examples of fixed effects, and then I'll probably pick up on that next topic, which will start after break, which is instrumental variable. So that we will spend a little more time on. It's a little bit trickier, but it's really using a lot of concepts we've already talked about, and in a unique way to deal with omitted variable bias, just like we can with fixed effects. It's just how can we deal with omitted variable bias without data when we don't have panel data. This is one way we can deal with omitted variable bias when we do have panel data. And really towards the end of the semester, and to your point in terms of exam questions, trying to give you a little bit more practice of like how would you actually apply this to data sets and how are we going to see this used in the real world. And so we will be doing a lot more work in Stata here for the remainder of the semester. Now, once we get back to kind of doing some more review, we'll dive into these things like looking at actual problems I would ask you on the exam. So we'll see that practice exam pop up, and then I think you'll have a little bit better of an idea of like what would the questions look like from this material. So I will try to get something up tomorrow, at least a first set of questions that you can start looking at for that final exam. I'll probably actually put it up in 2 parts. So I want to get some of those out there too early, and then as we cover more material, I'll kind of get you a second set that looks at more of that newer stuff that we. Other than that, any questions for me before I let you guys get out of here? All right. Try to stay dry the rest of the day, and I'll see you guys on Thursday.